This journal entry is Newton's laws of motion, specifically intended for my pre-AP students. It includes all 3 laws, okay? So this is not the journal entry for my regular students, but it's a good way for my regular students to review right before like maybe the midterm, like the quiz or midterm exam. Cut dotted lines only. Dotted lines only. You're going to have large chunks that are all in one piece. Dotted lines only. Starting with Newton's first law. First law is called inertia. Okay? So, here we go. Now, inertia of the law states an object at rest stays at rest, and an object in motion stays in motion at a constant velocity, and that will happen either stay at rest or at a constant velocity until an unbalanced force is applied. Okay? So the word inertia, it comes from the Greek language, and it means lazy. Now, Isaac Newton chose this word from the Greek language, inertia, because of the idea that inertia is a characteristic. All right? Inertia is a characteristic of an object. It's how much an object resists a change in motion. Okay? So, for example, the more mass it has, the more inertia it has. An elephant. Imagine trying to move an elephant. It's going to resist a change in its motion. Whether it's moving, trying to get it to change direction, or whether it's moving and trying to get it to stop, or whether it's at rest and you try to get it moving, it's going to take a lot of force to change its direction, to change its motion. Okay? Therefore, lots of mass, lots of inertia. Okay? The more mass it has, simply the lazier it is. So that's why Newton chose the word inertia, which is the Greek word for lazy. The more mass, the lazier it is. The less mass, the less lazy it is, the less inertia it has. So something as simple as this pin, it requires a very small force to get it to change its motion. Okay? So how much an object resists a change in motion is a characteristic. So you can say the inertia of an object. All right, so the notes here are to break down object at rest and objects of motion. An object at rest won't stay at rest. When the unbalanced force is applied to the object at rest, it starts to move. It accelerates. If it's 0 and it starts to move, that means it's accelerated. So the unbalanced force makes it accelerate. An example of an object at rest that wants to stay at rest is when you pull the tablecloth out from underneath the dishes and the dishes stay on the table. Okay? Classic sort of like a magic trick. The key to making that work is that your tablecloth needs to have very, very, very little friction. So like a silk tablecloth. The bottom of the plates need to have very, 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 very little friction as well. So they need to be very smooth at the bottom of the plates. And on top of all of that, you need the dishes to have lots and lots of inertia. They don't want to change. They don't want to move. So you need to have very, very heavy plates. And with that, you could make it work. We could get the conditions right. Minimizing the friction, maximizing the inertia of the dishes, and they will stay at rest. Okay? And the key also is that making sure that movement happens very quickly. And moving that tablecloth out. All right. Object in motion wants to stay in motion at a constant velocity. Okay? So this is an object that's already moving. That constant velocity, same direction, same speed, not changing. When an unbalanced force is applied, it will either speed up if that force is pushing it in the same direction it's already moving. It will slow down if that force pushes against the direction it's moving. Or it will change direction if that force pushes from any other direction. Okay? Any one of those things is technically acceleration. So if it will accelerate, decelerate, or change direction, all of those basically just mean it's accelerating. Okay? Those are all words that just describe an acceleration, because an acceleration is any sort of change in the velocity. If it has a constant velocity, that velocity changes. It's no longer constant. We have acceleration. It's either speeding up, slowing down, or changing direction. And that's acceleration. So an example, a baseball thrown in outer space, there's no friction out there. It keeps moving the same direction with the same speed. All right, so that's a constant velocity forever. Just keep going, 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 unless a new force acts on it. For example, out in space, the gravity from a planet. That would be a force that pulls on it, and thus changing probably its direction, maybe its velocity, immediate speed, depending on where that planet is. Probably changes both. Okay, so there we go. Wow, Newton's first law, inertia. Go ahead and get that glued in. So when you go back to look at these notes, a good thing to do is have some keywords highlighted. So the stays at rest, stays at a constant velocity until unbalanced force is applied. Okay? The word lazy there, that might help you remember what we're talking about here. And the characteristic is how much an object resists a change in its motion. All right, or a change basically in velocity. So second law, F equals ma. Before you glue that in and get soggy, go ahead and label it. F is for force, measured in newtons. M is for mass, measured in kilograms. A is for acceleration, measured in meters per second squared. Okay, if you don't have that memorized, you need to do so now. This is a statement that describes what the formula is telling us. It says that if a force is applied to an object with a specific mass, it will determine the acceleration. So the strength of the force determines the acceleration of the given mass of an object. Okay? So, what is that talking about here? Well, the key words here you need to learn: proportional and inversely proportional. Okay? The acceleration of an object is proportional to the force acting on it. So what does that mean? All right, let's say I have a really big force acting on a specific object. That will result in a very large acceleration. As one increases, the other one increases. As the force increases, the acceleration will increase. Okay? What if it decreases? What if we have a very small force acting on that same object, the object with the same mass? We'll end up with a small acceleration. Okay? If the force is big, the acceleration is big. If the force is big, the acceleration is big. If the force is small, the acceleration is small on a specific object. All right? So acceleration or force are proportional. However, acceleration and mass are inversely proportional. So, if we have an object with a really large mass and we apply a specific force to it, it will have a specific acceleration. But if we keep the force the same, but this time we change the mass of the object. So we're going to have an object with a small mass. That will result in a larger acceleration. So the forces are the same: large mass, small acceleration, small mass, large acceleration. So mass and acceleration are inversely proportional. As the mass gets bigger, the acceleration gets smaller. As the mass gets smaller, the acceleration gets bigger. Okay? This is something you already know. You will see some really awesome examples with this in the lab. So just keywords there. You need to know proportional and inversely proportional. Okay? So the acceleration and the force are proportional, whereas the acceleration and the mass are inversely proportional. Go ahead and glue those papers in. Important note here is defining force. So this little picture I like for helping define force. Force is a push, so like this guy pushing on that box, okay? Or force can be a pull. That guy is pulling on the box. Okay, force is any push or pull. So that's just a quick definition to include there in your notes for Newton's second law. All right, on to Newton's third law of motion. We are going to obviously be going to the OOPS page to put this in. Don't turn the page, just right there next to it, oops page. Okay? Third law, it's referred to often as the action-reaction, which I hate that definition. For every action, there's an equal and opposite reaction. Tells me nothing. All right? I rewrote the definition more effectively. So when one object exerts a force on another object, the second object exerts an equal and opposite force on the first object. We have equal forces, means they have the same magnitude. That's how they can be equal. And then opposite forces, the way objects can be opposite is that they're going opposite directions. Now the key to all of this actually making sense and working is that we must be working with two objects. Right? There must be two objects involved in this. It's easiest to think of two objects like that are stationary, at rest. Okay? We have a table and we've got a box on the table. We've got two objects. Now, the box on the table is pushing down on the table, and the table is pushing up on the box. Okay? Those two forces are going opposite directions. One's going down, one's going up. All right, and they're equal strength. So if this box is pushing down with 10 newtons, the table is pushing up with 10 newtons. These forces are equal strength, 10 newtons, opposite direction. One's going up, one's going down. Okay? That is what we're talking about with this action-reaction. Those are objects at rest. Okay? But if we have objects in motion, it still applies. Okay? So let's take a situation where we have forces applied and we can see the motion. The force will actually cause a motion. In our example of motion, we have these two objects. All right, these two people are both objects. Just a little bit of glue, so it just doesn't shift around. But don't make too much glue because we don't want gooey. All right, we have two objects, two people. All right, if you look at the arms, this lady, she's really strong and this lady is really weak. It doesn't matter. Look at, she's really fat, she's really skinny. It doesn't matter when we're talking about the force. Whoever pushes stronger, it doesn't matter. They will have, when they push apart from each other, it will be the same force. Now, if they're both really strong, that force would be greater. If they're both really weak, that force is going to be smaller. But it's the same strength forces are going to push these two ladies in opposite directions. And the reason why you're going to see them move is because they have the ice skates on. All right? The ice skates is basically the idea we're going to pretend we have no friction here. We're actually going to be able to see the force create. We're actually going to be able to see the force create a motion, okay, because of those ice skates on them, okay? But those forces are equal strength. Now, if we take this scenario and now we apply Newton's second law, okay, F equals ma, the forces are the same strength, okay? Forces are the same strength. But if you look over here, she's kind of on the chunky side, and she's kind of on the skinny side. So she is going to have a greater mass. She is going to have a smaller mass. But the forces are the same strength because Newton's third law says the forces are the same strength. So if the forces are the same but the masses are different, the accelerations are going to be different. The large mass is going to accelerate slowly, whereas the one with the small mass is going to accelerate at a much greater rate. So large acceleration, small acceleration, because this is a large mass and that one has a small mass. Same forces because of Newton's third law. Okay? Another favorite classic example of mine is the astronaut. Okay? If you ever watch the movie Gravity, this is the one scene in the movie I'm like, no! All right, so George Clooney, whatever his character's name I don't remember is, floating away from the space station with a constant velocity, so he has inertia, He has a slow, constant velocity, slowly floating away from the space station. Okay? But there's this big catch, and I'm like, but he should have saved himself. He could have saved himself because of this backpack. All right? We have a large backpack. At the moment, they are one object. But he can detach it and they will become two objects. Okay? So we're going to say that over here, and here we have the space station. The station. All right? We have over here our astronaut floating. All right? And he's going to take off the backpack. He's going to separate it from himself. Okay? They were one object, and now they are two objects. And he is going to use his intelligence, and he is going to use every bit of force he has. He's slowly floating that direction. All right, inertia, we have a constant velocity. But he needs a force to push him that way so that he can go the direction he wants to go. So that he stops floating that way and floats back the direction of the spaceship. All right? He only needs a force to accelerate him enough to a constant velocity in the opposite direction. So he's going to, with all of his strength, push his backpack away from him. He will push on his backpack with all the strength he has. His backpack is going to push on him with that exact same force. All right? Now his backpack has a smaller mass, so it will accelerate very quickly this way. He will accelerate slowly that direction. All right? So instantaneous push off, we're going to get him floating back the right direction with a very slow constant velocity, but eventually he'll get back to the space station, hopefully before he runs out of oxygen. Because we have two objects pushing off each other if he separates himself from his backpack. Okay? So that is Newton's third law. First law and second law, all in a quick summary.